fancy meter computers. How's everybody doing? This is the sound check portion of the class. Checking the sound. There we go. Good. Awesome, awesome, awesome. Excellent. Everything seems to be working Hi, I just transferred on. I'm hoping I didn't miss anything crazy Monday. Yes, if you haven't been added to the Avenue Shell, just shoot me an email, and I will be absolutely pleased as punch to let you in. If you you don't have to worry about getting on the teams just yet. That'll only really come into effect next week when we start talking about tutorials. Links in the syllabus. As your compatriots have explained, last class we just went over the course outline. If you have the time, I would highly recommend looking through the course outline / watching the last class if you haven't seen it, because it's a lot of very good, very important, very useful information. How is Felix? Felix is doing well. He's sort of ambling about the house, as is the volition of a 9-month-old. And wow, Remy was just right there, so I thought I'd grab her. This is Marimba. She's one of the 2 household cats. She hates being on television. But yeah, there we go. So anyway, so we might as well get right into it then. Normally, the I'm gonna try to make more of an effort to keep things on track this semester. So expect us to start class actually right close to when it starts, eh? Okay. Yeah, she's sweet. She's a bit of a princess, though. So. Oh, no. I was told by my wife's family, they're Italians, and they say anything that people consider unlucky can also be lucky. So she's our lucky black cat, according to Italians, at least. So let's talk about programming, shall we? When is the Hexy Hashy Let's Play? Check the channel. I've done one in the past. And besides, the pinball game sells much better. Oh, poor guy. Alright. So. Programming. Welcome to Computer Course. In this class, we will be discussing programming. If you have no programming experience, don't worry. This is still the class for you. Please don't... I said this last time, but I'll say it again because it bears repeating. Don't be discouraged if you're taking this class and you're looking to the person next to you and they're playing Crossy Roads on their phone, not even paying attention, and then you see that person getting straight A's on all of the assignments. Because this program, because this course starts you from the very, very basic beginner stuff, yet is a required course for a bunch of the other comp sci courses, and the university doesn't really accept individual learning as being real learning, I guess. Basically, there are going to be a bunch of people in this course that already know how to program, so please do not judge yourself by people who have already been programming for, 10 years. Judge yourself by how much you've learned and how much you've grown over the course of this course. So for VPN stuff, please talk to the TAs, or not during class. Just to clarify, Jupiter is still under construction. I think ask Mark Hutchison. He's the one who knows. Yeah, the login for Jupiter will be your Mac ID. So programming. So what is programming, right? In general terms, we all know that programming is important, an important skill that you can use to, you know, you can use it in various aspects of your life. It turns out that programming is actually an extremely useful skill anywhere that you're having to deal with data, right? So anytime, like, and, you know, basically anytime you're working on a computer doing tasks that could be automated by the computer itself, knowing how to program is a way that allows you to access, you know, greater levels of automation from the device that's sitting right there in front of you. By writing programs to handle data, you don't have to handle it yourself, which means that you get to take more coffee breaks, basically. So what is programming? Well, to know what programming is, you kind of have to know what a computer is, right? A lot of people these days kind of, one gets the impression as a computer science professor that a lot of people these days kind of think of computers as being these like black boxes. I always make jokes about cell phones as them being magic rectangles because, you know, the overwhelming majority of the people who use these programmed electronic devices don't actually understand even the smallest part about how they work. You know, it's just, you know, tap not work, phone bad, throw, you know? So a computer runs software. That software is a sequence of instructions, right? These instructions are coded in a language. The language that you use to encode programs on a computer is known as a programming language. The internet is just a black box with a red LED. Why can't my computer be? It can be if you want it to be, but it's more useful to you if it's if you have a little bit more, you know, high level, like a little lower, a higher resolution view of what's going on inside of it. So essentially, when you create a program, what you're doing is you're creating a list of mathematical instructions and operations that the computer performs sequentially in order to perform some task. In this class, most of the tasks we're going to be talking about are, roughly speaking, mathematical. This is just simply because it's easier to step into programming from associated skills like algebra than it is to sort of, you know, start working on the sorts of programming that, you know, you would do in a, you know, in an actual job programming, right? So basically this course has a lot of math problems in it. But yeah, so essentially what you're doing is you're creating a series of instructions that take some input and produce some output. Those of you who remember anything you may have taken on computers from elementary or high school will know that the concepts of input and output are extremely important when it comes to computing. Everything you do in a computer should be conceptualized input, process, output. So, let's consider a mathematical problem. Or a few mathematical problems. So, question. What is the square root of 25? Obviously, it's 5. What is the square root of some number y? The square root of y is some number x such that x times x is equal to y. So, we've taken this this question and we've broken it down in terms of some components, right? As we're going to see, you can actually derive an algorithm for computing such a thing by searching possible values and waiting for a condition to be true. And you can actually write an algorithm that finds the square roots of numbers. This is enough of a description to write an algorithm on, basically. How were people able to program the functionalities of programming softwares? Ooh, how are the inputs hardwired to be pieced together to create the outputs? Well, so I think what your question is kind of getting at there is like, who shaves the barber, right? If we have all of these programming, if we have all of this programming code, how does programming code come into existence? And the answer, of course, is more programming code. All of you listening to this through your computer screens right now should feel very, very privileged to be the inheritors of, I would say, over 100 years at this point of hard development and engineering work that has resulted in the modern computer. Essentially, how computer development has kind of gone over the years is you design a computer, right? And the very first computers were designed by hand, right? You design a computer. You use that computer to help you design the next computer. You use that computer to help you design the next computer. This is a process that's known as technological bootstrapping. So, essentially, pardon me, had a hair in my mouth. Essentially, the development of the modern computer has been a 100-year project that has had a number of sequential, vast improvements in technology and computer design. And the more computer we had, the more computer we could use to help us design the next computers. So now, that's kind of how things build up over time. Essentially, solid-state electronics were a big improvement. That allowed the invention of the microcomputer, which everybody just refers to them as computers now, but at the time they were called microcomputers because you didn't need a whole room for them. Most of you are probably aware that, back in the 1950s, a computer device took up a whole room because each of the electronic switches that make a computer work, each of those had to be a physical vacuum tube, about, yay big. So obviously the thing had to be huge. Once we discovered the properties of solid-state electronics and doped silicon, doped with various atoms that affect the electrical charge, essentially, if you want to know what a computer is, right down at the fundamentals of the electronics, right? A computer is just a series of switches, right? I don't answer questions should I be taking notes on this. If you don't think this is important enough to pay attention to, then don't pay attention to it. I'm not your mother. So essentially, everything, if you take a computer and you boil it right down to its essential components, you get what are called transistors, right? A transistor is essentially just an electronic switch, right? You have 3 lines coming into a transistor. One line controls the flow of electrons between the source and the sink. So you can turn the flow of electrons on or off. From this, you can build logic gates, you can build processors, you can build memory components, you can build pretty much anything. This is sort of the fundamental layer of the computer. So what you have then is you have the quote-unquote central processing unit. The central processing unit implements in these transistors various commands, right? A big processor like an Intel processor will probably have several thousand commands. When we program, we write something in a language which is interpretable to human beings, and a software process converts that program into these machine instructions. We're going to get to this later on in this lecture, or later on this week or something. Pardon me for just a moment, folks. Yeah. There we go. So, it's not necessary for you, the programmer, to know exactly how the program is being broken down into the machine code, into the actual CPU instructions, right? That's not necessary for you to know in order to be able to program a computer. What is necessary for you to know is how to effectively use what we programmers call the high-level language. High level in terms of abstraction. So in this class, we're going to be studying the Python programming language. Python is one of these abstract programming languages that gets broken down into a very large number of very small CPU instructions, which can be run very, very quickly. A modern CPU is capable of executing something like 4 billion operations per second, something like that. So you just whatever the number of gigahertz your processor is, that's the number of that's roughly speaking the number of operations that your CPU performs per second. So let's examine an actual problem, shall we? And we'll come up with a formulation of this problem that we can put into a computer. So let's consider the problem of finding the x-intercept of some function f. Let's say this, we don't necessarily need to know what the function is to be able to do this. All we need to do is to be able to test points on it. But there's also instructions per cycle. Yeah. I said roughly, didn't I? And besides, this is intro. Fetch, decode, execute. But you can pipeline them. So let's say we had a function f, which is monotonically increasing on some interval ab. All that monotonically increasing means is that for any point on this function, say we had 2 points x and y and two values of the function at x and y, f of x and f of y. If x is less than y, then f of x will be less than y of x, and vice versa. So all that means is that this thing goes up without going down, right? It doesn't inflect at any point. So to determine the x-intercept with some precision epsilon greater than 0, and people traditionally have a problem with the concept of epsilon. So the idea is that we're not finding the precise x-intercept. We are finding the x-intercept within an interval. Half the size of that interval will be called epsilon. So I have a request in the chat to say that again. If you want to hear me say it again, run the video back. We must press on. If I'm talking too fast for you, you can also watch it back afterwards at 75% speed. Or if I'm not talking fast enough, you could run it back at 150% speed or something like that. So this interval is non-zero. So basically, we're trying to hit an x-intercept somewhere inside of this window, right? So this is the algorithm. So long as b minus a is greater than epsilon, do steps 2 to 4. Step 2, calculate m, which is the midpoint between a and b. So we want to know what the x position is of the midpoint, right? We then test to see if f at m is less than 0 or greater than 0, right? So in this example, f at m is greater than 0. If it's greater than 0, then we know, because f at m and f at b are both above 0, we know that if this thing crosses 0, then it needs to do so on the interval am, right? Conversely, if this f at m is below the line and b is above the line, we'll know that the intersect has to occur on the interval mb. So If it's less than 0, you set a to m. And if it's greater than 0, you set b to m. The result is you can then apply the same algorithm to that now reduced problem, right? So let's take a look and see if we can't perform an implementation of this. So I want to get you guys into the code right away. This is not code. This is a bash command. This is a command prompt. I'm using a Linux operating system, so yeah, you'll get used to seeing me use command line stuff. Make directory examples. Change directory examples. You don't have to know this. If you want to, like, if you take 1xc3, you'll learn this kind of stuff. So get it topic 1.py. There we go. So this, we shall write our program. If you do this an infinite number of times, will a equal b minus the intercept? See, the problem... Okay, Daniel, I'm going to adjust your thinking here, right? Because that's actually a very common way of conceptualizing things from a mathematical point of view, right? It's like, we take a process, we repeat it an infinite number of times, and this will be the result, right? That's how series work. You don't have that luxury when you're operating a computer system. A computer is a physical entity. It is a physically constrained entity just the same as we, right? So a computer cannot run a program to infinity even if it wants to, right? A computer does not have an infinite supply of memory. So let's do this, right? Define function. Def, we'll call this intersect. We'll take a function f and some interval a, b. Right? So, step 1, we have to test to see if we're done. We have to test to see. Oh, we'll also need epsilon. There we go. We'll have to test to see if this first condition comes out to be true, right? So, if b minus a is greater than epsilon, then we'll do the rest of this. Otherwise, we will return a and b. So, next we have to calculate m. So m is equal to a plus b. For those of you who have some previous programming experience, this may be the first Python you have ever seen. Note the lack of semicolons. I already explained epsilon, so run the video back. It's the error, right? So we're only interested in finding the x-intersect within some margin of error. Epsilon is that margin of error. So, if f at m is less than 0, we do something. If f at m is greater than some other thing, we do something else. That's the choice. So, there are two ways of going about this, and I guess I'll show you the easy way first. The easy way would be to, rather than do this in an if statement, embed it inside of a loop. So while b minus a is greater than epsilon, that will take everything inside of here and repeat it until this condition is no longer true. We say a is equal to m. Otherwise, b is equal to m. Come on. There we go. And there we go. I believe that'll be everything. So, it's not sufficient to just define the function, however. You also have to use it. So first, let's define some function f. Say f1 takes x, return x to the power of 3 minus 5, or to the power of 2 minus 5. There we go. Good, good, good. And then print intersect of f1. Let's say from 0 to 10. We know that it should be somewhere inside that interval. With an epsilon of 0.0001, let's say. There we go. This is a program. This is actually a full and complete Python program. So let's execute it. There we go. So from the command line in Linux, to execute a Python program, you simply type python3 and then the name of the file, which in this case is topic1.py. So you can see the results that this program produces is the x-intersect is somewhere between 2.236022, etc., etc., and 2.236099, etc., etc. So you can see that we are accurate within the specified epsilon. If we want to find it more accurately, we simply increase the size, or we make epsilon smaller. So you can see that there's a greater degree of agreement, so to speak, between these two numbers. So there you go, your first program. Ta-da! So let's explore this program just a little bit then. So one very powerful way of debugging programs is you can use print statements to view intermediate results. But I think just because I have 150 watching, which is probably, it's kind of funny, but like with these types of courses, I can say this is the most people that will ever watch this lecture, and every single lecture that will be true. So I'm going to show you Python Tutor. So this is pythontutor.com. It's a website which I highly recommend you become familiar with. What it does is it allows you to program in it, and then it allows you to view how the data is changing that you're operating on as you operate on it, which is extremely useful. I highly, highly recommend using Python Tutor. So let's just copy this program over and maximize, visualize. I really thought the first program would be easier, like Hello World. I mean, okay, you want Hello World? I'll give you Hello World. Fine, done. There you go, Hello World. Hello World, there you go. That's how you make the thing say Hello World. Uh-oh. Am I losing the feed? Looks like we've got it back. Okay. Yeah. So, yeah, this is, like, I'm not expecting you guys to be able to do this right out of the gate. I'm demonstrating how a program works, right? So, does f at m in the code tell Python f is a function? Yeah, essentially. So Python has this thing called duck typing, which is if it walks like a duck and it quacks like a duck, it's a duck. That is to say, a thing is how you use it. So because I'm applying an argument here to f, that essentially casts it as a function. That code doesn't seem optimized for Hello World. Well, nothing else is being run, right? I'm just defining a useless function or two. So when we enable, when we start up this operation of this function, right? So f is this function. A is 0, b is 10, epsilon is small. I guess it's showing up as small. I'll edit it so that it actually shows up properly. We'll do it that way. Hopefully then it shows up. Come on! There we go. So, we're in this loop. We continue in this loop. We now have m. M is 5.0, right? So the return, so if we calculate the value of the function at that point, that'll be 20. That gets passed back to the function. So we enter and set. So we skip over this one. It would be slightly more efficient here if I were to pull this function call out here, but it doesn't really matter. So this condition passes because this is greater than 0. We then execute this line of code, setting b equal to the current value of m. There you go. Now we recalculate m to 2.5. This continues. Still greater than 2.5 is f at that value is still greater than 0, so we replace b again. Next m is 1.25. The value of the function at that is negative, so we set a up. And you can see that continues and continues and continues until such time as we reach some kind of, until basically this condition fails. So when the difference between a and b is less than epsilon, that breaks the loop and returns the result. And that's how the algorithm works. Of all the extra resources on Avenue, what would you say is the most beneficial right now? Coding bat. Do you need to declare the variable type when you make a new variable? Not in Python. It's Wild West programming. So, there you go. So, what happens if f at m is equal to 0? As the thing is currently written, it would flop out. That would actually result in an infinite loop. So what I would do is I'd just put a little equal sign there. But thank you for catching that bug. So, what if epsilon is equal to 0? That would also result in an infinite loop. Basically, the interval b minus a will never be able to reach 0 for computer engineering reasons that we'll be discussing later in the course. We'll actually be revisiting this problem later in the course, so please hold your question until that point. So, let's talk about the differences between declarative and imperative descriptions. So, when you're talking about programming languages, they can be roughly classified into a bunch of different categories. One of the major categories is, are you dealing with an imperative language or are you dealing with a declarative language? Python is an imperative language. So, imperative descriptions tell you how the result is obtained given a sequence of instructions. Declarative descriptions describe the properties of the result, and you can just let the computer figure out how to get it. Yeah, so if you didn't understand this example, the point was not that you could follow I'm going to take the time to introduce to you in detail all of the constructs that we used in this example, right? We're going to have slides on everything I used to produce that solution. I just think it's really useful for you guys to see what a program looks like and how it's programmed once you know what you're doing. That's kind of like the intro level we're at right now, right? We still haven't really talked about anything yet. So, declarative descriptions, you just say what the answer should be and let the computer figure out how to calculate it. Under imperative descriptions, each step must be simple enough that it can be followed. So, one way or another, imperative will ultimately map onto the CPU instructions that underlie everything. The CPU itself requires imperative description. That is the mode of calculation of a central processing unit. Declarative languages always eventually get translated to imperative anyways, but they can be slightly easier for humans to use. So setting eps equals 0 is like the equivalent of doing an infinite amount of times to get an exact value, which a computer can't do. Yes, that's a good way of thinking about it, Daniel. Yes, absolutely. So let's talk about algorithms. An algorithm specifies a sequence of instructions to be executed by a machine that, when provided with an input, will eventually stop and produce some output, if you're lucky. Can you give an example of declarative languages? So Haskell is a declarative language some of you may be familiar with, especially if you're more related to the comp sci program. Prolog is a declarative language. I think R is a declarative language. It might be. But yeah. So let's consider algorithms, right? Algorithms in very general terms. A cookbook recipe is an algorithm. The machine on which that algorithm operates is the human in combination with any of the kitchen tools and appliances they're using to cook, right? The input to that recipe is ingredients out of your fridge or can or wherever you're getting your ingredients from. And your outputs are delicious, delicious food. So the instructions that are being followed by the human being, kitchen combination machine, are the instructions as written on the recipe card. And as all of you, I'm sure, know, if you've ever tried to cook, the more explicit and thorough the instructions are, the more likely you are to result in the food being edible. Another example is a traffic light. So for traffic lights, inputs can be time or car presence sensors. The instructions would be actual programming code that's sitting in some box that's adjacent to the traffic lights. And the machine upon which those instructions are being executed is, of course, the combination of the traffic lights themselves and the controlling mechanism. And the outputs with the electrical signals to the light bulbs are the outputs from the controller's perspective. From a physical human's perspective, the photons emitted from the traffic lights are the outputs of that system, which are then received as inputs by your eyeballs and processed by the machine that is your brain into either stop or accelerate pedal depressions in your vehicle. Your vehicle then takes pedal depression / steering combination as the input to that machine. The machine, the engine, and all of the associated apparati are the machine upon which those inputs are operated by instructions which are encoded mechanically via mechanical parts, and the output to that system is velocity and position. So you can see everything can be an algorithm if you think about it that way. When I was young, I always thought some guy in a room was controlling the traffic lights. Yeah. It's like Flintstones-o-vision, right? Anytime you had a sufficiently complicated appliance or something, there's just a tiny dinosaur in it that's actually running it. So we are living in a Python code. Python program, and no, there are many, many other languages, not just Python. This isn't really, from a philosophical standpoint, this is, of course, only one way to conceptualize the way that the world works, right? You should think of algorithms and algorithmic thinking as a conceptual tool with a limited domain of applicability. For example, algorithms are not very effective at predicting human behavior. Human beings are notoriously difficult to predict. As Dostoevsky said, we are not simply keys on a piano, but yeah. So we're living in a. I did not say that we're living in a simulation, but if you want to think that, then I can't stop you. How was the first language created? I don't know, actually. The first languages were on punch cards. We'll get to it. So, the computation prescribed by an algorithm goes through a sequence of states, starting from an initial state, and with each instruction leading unambiguously to a new state. So, if you perform a trace, what you're doing is viewing the intermediate states of the program. So if we pull back the Python tutor example here, this timeline that I'm sliding through that allows us to view all of the different values after each instruction is executed. These are states. Every tick on this slider is a different program state. By viewing the internal states of the program, we are performing a trace of that program. I also didn't say we weren't living in a simulation. I mean, if we were, would it really make that much difference, honestly? So, if you're wondering where the word algorithm comes from, it comes from the 9th century Persian mathematician Al-Khwarizmi, sorry if I butchered that, who published an arithmetic treatise on calculating certain values. The Latin translation was called Algorithmi de Numero Indorum, or the Algorithmi on the Numbers of the Indians, which of course was hilarious, because he wasn't from India, he was from Persia. But yeah, the word algorithm is actually a guy's name. It's kind of interesting. The word algebra has a similar origin. I just would like to say that throughout the Middle Ages, the Islamic world was just knocking it out of the park when it came to scientific advancement. They were really pulling the whole rest of the world up behind them. There's a reason that we use Arabic numerals. So, properties of algorithms. Algorithms need to be executed mechanically, particularly those as applied to computers. Thank you. So, an algorithm must be precise, and it must be effective. Precise means that it's only possible to reach one next state from the previous state, right? If you can reach more than one next state from any previous state, you have what is called an indeterminate system, or a non-deterministic system. Generally speaking, this is to be avoided. Unless you're dealing with like quantum computing and quantum superposition or other esoteric forms of matter. Algorithms must also be effective. So the machine must actually be capable of executing each instruction that is being performed, right? Or that you're asking it to perform. So it's like, if you have a computer and you say, set X to 3, set Y to 7, make me a cheeseburger, 2 of those instructions the computer can execute, the third it cannot. The computer cannot make you a cheeseburger. So it's useless to try to ask it to, so that would not be an effective algorithm because it could not be put into effect. So, though I'm just going to skip those because they're not important. I've been meaning to pare these slides down. So, here are some fundamental questions about algorithms. I closed the door, but he's still trying to get in. That means you're superior to a computer. I mean, you might be. You're certainly superior at interacting with physical stuff. But, when it comes to processing very simple mathematical operations in very quick succession, a computer will beat you, I'm afraid. So generally speaking, when we are talking about algorithms, there are two main points of concern. One is the algorithm correct? And two, is it efficient? Right? So, correctness. Yeah. Correctness is, whenever we ask, is this algorithm correct? There was an insane AI robot at CES this year. Yes, well, I'm not saying that the computers aren't making, aren't gaining ground against us. That's it's still cheaper to make a human than it is a computer or a robot. Pardon me. So when we ask if an algorithm is correct, what we're actually asking is, did we get out the expected output for particular input? This is, we're going to talk about this more when we talk about testing. But in general, to determine the correctness of a computer algorithm, you have to have what are called specifications. So you have to have some kind of document somewhere, or some person who really knows what they're doing, that somewhere the relationship between the input and the output must be encoded in such a manner that you can check the output of the algorithm when it's produced. So you need some way of verifying that the algorithm actually works. Second consideration is efficiency. How long or how much memory does it take for this algorithm to actually execute? How long does it take to produce the output for a particular input? We measure this in terms of time. We measure this in terms of the number of instructions. We measure this in the worst case, best case, and on average. We can also do amortized analysis. And we also are concerned, again, with how many resources are occupied by this algorithm. Obviously, you can have the most correct algorithm in the universe, but if it's so inefficient that a computer can't actually execute it in your lifetime, which, believe me, actually happens more often than you might expect, that's still a bad algorithm, right? Generally speaking, the types of algorithms you'll be producing in this class will be sufficiently short that none of them should take more than a small fraction of a second to execute, with a couple of exceptions when we're really trying to test you. But yeah, so I kind of already answered this question because one of you asked it in the chat, but can we compute the exact x-intersect by taking epsilon equal to 0? And the answer is no. We would result in an infinite loop. That would not, the efficiency of that algorithm is sufficiently bad that we would not be able to execute it in general terms. So, there we go. Next time in class, we'll be talking about the actual building blocks of programs. We'll be talking about if statements, while loops. We'll be talking about variables and assignment statements, all of the fundamental building blocks of code. So, thank you very much. If you have any questions, I'll take them in the chat. Otherwise, yeah, that's it. Are there tutorials this week? No. Excellent. Excellent, excellent. See you guys on Friday. Will you be going over the code you did today in more depth? I mean, line by line. Probably when we revisit it. We save local Jupyter programs as .py? No, it's .ipynb. It's IPython Notebook is what it stands for. But no, the file extension for a Jupyter Notebook is .ipynb. Just don't modify the file extensions. Don't modify the file names either. Just don't put your student name in the notebook file or name or anything like that. Just submit it as is. We'll know it's yours because it'll be in your submission folder. What needs to be done before next class? Nothing. See you next class. To follow up on last statement, if x was rational, would it be reached? I don't know what that's in reference to, Daniel. When do you have to download pip by? I would recommend Anaconda rather than pip. It'll include pip, actually. Whenever you want to start working on the assignments. Classes are online until the 31st, right? Yes, correct. If we have the textbook, what pages would be ideal for this week, if applicable? Oh, there are, there should be, reading, weekly readings should be on Avenue. Let me take a look. See if they made it through this semester. Yep. On Avenue, I've got the weekly readings, so just check out that, and that's my recommendations for what to read in the textbook. Will I still be recording lectures when we return to in-person learning? I will. Now, him crying that like that is basic. I got the door closed, so it's basically him saying like, "Let me in, let me in, let me in. I want to be part of the fun." Cool. Something on the slide. X. Oh, I see. Your question is like, what if you actually do end up with like an exact reading? You can always put a case in to handle that, but as we're going to see when we study floating point numbers, it's actually a lot, like, you basically shouldn't assume exact value, that you'll ever get an exact value with a floating point number. And if that doesn't make sense, that's fine. We'll talk about it in topic 6. Take her easy, folks, and don't do anything I wouldn't do. Can you use a Mac device for this course? You absolutely can use a Mac device for this course. You can use any computing system. You can use a potato if you have one. As long as you can get a potato to run Linux, then you can use a potato. I say Linux because it's the lightest weight of all of the operating systems. Take her easy, folks.